Good day. My name is Arlen Mendoza, and I am a mathematics professor at Pangasinan State University, Philippines. As part of my academic work, I have conducted research on test item analysis, a method for evaluating the quality of test items used in educational and psychological assessments. Test item analysis is a valuable tool for teachers as it provides important information about the quality of tests and helps identify areas where students may be struggling. Furthermore, it is crucial for ensuring that assessments are fair, valid, and reliable measures of student learning. My research was conducted across 9 campuses of Pangasinan State University, located in the province of Pangasinan, specifically in Alaminos, Asingan, Bayambang, Binmaloy, Infanta, San Carlos, Santa Maria, Urdaneta, in the main campus in Lingayen, Pangasinan. This research was entitled Assessing Test Item Quality Through Differential Item Functioning, a Mantel-Haenszel chi-square statistics approach. The Mantel-Haenszel chi-square statistics approach is a non-parametric statistical method that is commonly used to detect differential item functioning or DIF in tests. DIF refers to situations where groups of individuals with the same underlying ability level perform differently on certain test items due to factors unrelated to the construct being measured. In the field of educational assessment, it is crucial to guarantee that all test takers are given a fair and equal opportunity to demonstrate their abilities. The responses of each individual should be based solely on their innate level of skill and knowledge and not be influenced by any external factors. This means that the test should be free from any biases, such as those based on demographic characteristics like gender, ethnicity, socioeconomic status, or educational background that could affect test takers' performance. In the past year, there has been increasing concern and criticism around standardized testing, particularly regarding the issue of test inequality. This issue has been highlighted by Miranda in 2020 and has sparked widespread debate and discussion. Jones in 2019 has conducted a review of the issue and found that DIF can lead to biased assessments of group differences, which can have a significant impact on research outcomes and risk factors. DIF occurs when different subgroups of test takers have different levels of performance on a particular test items, even when they have the same ability level. This can result in certain groups being unfairly advantaged or disadvantaged by the test, which can compromise the validity and reliability of the assessment. The evaluation of biases in testing is a crucial area of interest in the field of psychometrics, and DIF analysis has become a popular tool for this purpose. DIF analysis allows researchers to identify any potential biases in test items by examining whether different groups of test takers who have similar levels of overall ability respond differently to specific items. Despite its usefulness, the complexity of DIF analysis has been a significant barrier to its adoption by researchers who are less mathematically inclined. This has resulted in a limited use of DIF procedures in research. The limited adoption of DIF analysis is problematic as it can lead to biased assessments that produce inaccurate or unfair results. To address the limited adoption of DIF analysis, it is essential to make efforts towards enhancing its accessibility. These efforts could involve the development of clear and concise guidelines for interpreting DIF results that could help researchers make sense of the findings and use them to improve the quality of their assessments. The primary aim of the present study is to improve the development of fair and unbiased tests by providing valuable insights into the into the use of DIF through the Mantel-Haenszel chi-square statistics approach. To achieve this goal, the researcher used the Mantel-Haenszel approach to identify bias items in the mathematics achievement test based on various student characteristics, including age, sex, socioeconomic status, and school type. By identifying these bias items, the study ensured that the test is fair and equitable for all students, irrespective of their background. Furthermore, the current study aimed to improve the reliability and validity of the test by identifying and removing items that exhibited significant DIF using the Mantel-Haenszel approach. The reliability and validity analysis were conducted using established psychometric techniques and provided vital information about the test quality after eliminating bias items. The research employed a descriptive research design to assess the performance of students in mathematics. The study evaluated all students who were enrolled in the secondary education program with a major in mathematics and who had already completed the calculus subject. To collect the required data, a structured questionnaire and a 100-item achievement test in calculus were used. To analyze the test items, the DIF method was applied, specifically utilizing the Mantel-Haenszel chi-square statistics approach. This approach allows the researchers to gather important insights into the quality of the test items and to identify areas where improvements could be made. Pidragita proposed a classification system to categorize the degrees of DIF items. DIF in test items into three levels, which are referred to as A, B, and C. The categories are defined as follows. Items that are flagged as A exhibit negligible amounts of DIF, with the absolute value of the Mantel-Haenszel delta, or MHD, significantly differing from 0 but smaller than 1. Items identified as B exhibit moderate levels of DIF, with MHD values significantly differing from 0, and either the MHD being not significantly greater than 1.0 is smaller than 1.5 in absolute value. Items that fall into category C display large amounts of DIF, with the absolute value of the MHD being greater than 1.5 or significantly different from 1.0. The following table summarizes the findings of the DIF detection analysis using the Mantel-Haenszel statistic. The data reveals that out of the 100 original items, 32 displayed DIF and were detected through the analysis. Furthermore, the table shows that DIF was more commonly detected based on age differences. Additionally, bias items were also found based on sex, socioeconomic status, and school type. The graph depicted in Figure 1 visually represents the deviation of each item's value of the Mantel-Haenszel chi-square statistics from the critical value. The items highlighted in red indicate those flagged with Mantel-Haenszel with higher chi-square statistic, obtaining a very significant value of less than 0.01. According to the results of the study, a total of 23 items showed bias towards a specific age group, specifically 4 items. Items 8, 16, 37, and 96 were potentially biased against the focal group, those aged with 17 and below, while the remaining 19 items showed potential bias against the reference group, those aged 18 and above. The analysis revealed that the reference group may face potential bias with a higher number of DIF items, implying that individuals age 17 and below were disadvantaged on these items. On the other hand, the disadvantaged group, age 18 and above, appeared to need more effort to succeed on these bias items and improve their performance. Based on the results, both groups have the same ability level but perform differently on the DIF items, suggesting that age may affect success on these items. These results somewhat confirm that children and adolescents tend to have better memory retention than adults due to the continuous development of the brain and neural connections during this stage of life, as according to Echobon and Christis et al. In 2017. However, to avoid bias in the test, revision should be made to suit the age differences between the two groups. The presented table displays the four items that exhibit potential bias against the focal group of examiners. These items obtain the highest estimate of DIF degree and may disadvantage the group of examinees age 17 and below. On the other hand, the results revealed that more DIF items were potentially biased against the reference group, that is, the group of examinees age 18 and above. 19 items were detected, and the topmost items with the highest Mantel-Haenszel chi-square statistic value were presented in the given table. It can be gleaned from the table that all the DIF items detected were categorized as C, which means that these DIF items had large effect and were recommended for strict revision or to be replaced. Other items not included in the table were under category A and B and had not been detected with DIF but were visible in figure 1. Based on sex differences, the analysis showed two bias items. The study identified potential bias against the reference and focal groups in items 37 and 72 respectively. Considering that these students have the same level of ability, findings only show evidence that additional examination and research are required to comprehend and resolve potential sources of bias in the Mantel-Haenszel analysis relating to sex differences. Okay. Moreover, findings showed significant relationship between the success of students on items 37 and 72 and their sex differences, supported by a p-value lower than the significance level of 0.05. Additionally, the two identified DIF items were labeled as C, indicating a potential substantial impact on the overall test. It is noteworthy that these items were also identified in the Mantel-Haenszel analysis based on age differences, which provides further evidence of their potential bias. Based on socioeconomic status, the analysis revealed that items 47 and 86 exhibited DIF with a severity rating of C, indicating a significant degree of DIF. A potential bias against the reference group, that is, students with a monthly income above 8,000 pesos, was suggested by the larger Mantel-Haenszel DIF value observed for item 86. These students had a harder time succeeding on this item. Furthermore, the item's significance value was notably high, indicating a significant relationship between the socioeconomic status differences of students and their chances of succeeding on the item. On the contrary, item 47 appeared to be disadvantageous for the focal group, which comprised students with monthly gross income below 8,000 pesos. The results depicted in figure 3 corroborate those presented in table 4, where black items denote DIF-free items in the Mantel-Haenszel analysis based on socioeconomic status differences. This suggests that socioeconomic status differences also significantly affect the overall test performance of the students. Table 5 shows that 5 test items items 44, 43, 59, 55, 33, had significant DIF based on school type differences, with severe DIF indicated by their C category ratings. The focal group is specifically students from public higher education institutions or public HEIs had difficulty succeeding on these items, indicating potential bias against this group. Differences in curriculum, instructional practices, or student background in both private and public HEIs could contribute to these differences in student performance. However, eliminating bias items due to school type differences may help address these issues. Figure 4 provides a visual representations of items with potential bias based on school type differences, which is evidenced by their notable deviation from the detection threshold line. This suggests that these items may be functioning differently for various groups of students, potentially resulting in biased test results. Table 6 provides information on the reliability and validity indices of the updated mathematics achievement test. The construct validity coefficient of the revised version of the test indicate that it is a well-designed test and represents a single dimension. The concurrent validity coefficient of the revised version revealed a significant positive relationship between the test score and the GPA of the students in their math subject. The content validity, on the other hand, of the revised version are within the acceptable levels, and the evaluators judge the test to be valid. And moreover, the data presented in Table 6 indicate that the revised version of the test exhibited a reliability coefficient greater than 0.8, indicating that the set of test items is strong and possesses a reliable scale. With the obtained findings, this study concluded that factors such as age, sex, socioeconomic status, and the type of educational institution could influence the disparities observed in students' performance on the examination. Age, in particular, played a significant role in these variations. The study also concluded that the removal of potentially biased items has led to a more equitable and valid assessment. Therefore, it is recommended that external factors such as age, sex, socioeconomic status, and the type of education institution should also be considered when interpreting the examination results and implementing measures to address student performance inequities. Taking these factors into account can lead to a more accurate and comprehensive understanding of students' academic performance and better informed decision making in educational policy and practice. In addition, it is recommended to use the Mantel-Haenszel chi-square statistic in other contingency tables or item response tree techniques for conducting differential item functioning analysis to assess the equity and credibility of educational evaluations. The conduct of this method in evaluating the quality of test items could improve test fairness, increase validity and reliability of tests, and promote social equity. So these are my references. Thank you very much.